Bismillahirrahmanirrahim. Good afternoon, everyone. Today we will explain together the important information about forward applied bias. By starting from the title, let's go to the next slide. Here, let's me use this diagram, this figure, this image. Here we was dealing with normal p-n junction, and after that we connected with AC power like battery, and after that we dealing with important condition to reach forward applied bias. That will be by put this terminal connect it with the negative terminal power, and after that put the positive side with the P region. That's mean here we're doing the different 100% things compression than the reversed biased. At reversed biased, the plus side with N region and negative side with P region, because that we must be careful. And after that, what will happen? We will explain all this information together, how the holes at the P region, the majority at the P region started to travel, to moving by crossing the depletion region to N region, and after that, how the majority at N region started to moving to P region by crossing the p-n junction, and what will happen with the depletion region, WD prime here. I put it a prime here because we're dealing with another depletion region like we're seeing here. The depletion region is different from the forward bias, zero bias, different from the normal p-n junction without any connected with any power, with any battery. Please come back to the second slide. Forward bias p-n junction. A negative voltage, like I said before, is applied to the N-type material, and the positive voltage is applied to the P-type material. We connected these terminals like that to can reach the forward applied bias. If the external, here we will dealing with important condition. Here the external voltage must be greater than the value of the potential barrier. That's mean B bias voltage, external voltage, must be bigger than V bar, barrier voltage. Why? To make the potential barrier, V bar, opposition will be overcome and current will start to flow. This important thing, let's put this statement between two brackets. All that to can let the current start to flow. This will be by dealing with this condition, the potential barrier must be bigger than barrier voltage. V bias must be bigger than barrier voltage. Why? Let's answer this question. Yes, after that, yes. Why? Why the depletion region now is be like smaller than? Why the electrons start, the majority in the N region travel to the P region, and the opposite? Why the majority at the P region started to travel to N region? Because the negative voltage push the electrons. Here we're talking about inside or specifically in the P region. Because the negative voltage push the electron toward the junction. That means help them to can cross the potential barrier to kind of cross the depletion region to the another side, giving them the energy to cross over it. Give them the necessary thing, and this necessary thing is the energy to can be bigger than the potential barrier to kind of cross the depletion region, and combine with the holes, and the holes voltage push the positive charge, positive voltage push the holes toward the junction, by giving them the energy, the important current, the important power to kind of cross the depletion region to another side. Let me explain that. Like here, when the majority in P region start to go to the N region, and the electrons traveling to P region, like that. Here, this is the most important slide here. Here, to can imagine this diagram, we have two important tools: the power, the voltage power, and the emitter. Emitter will calculate very small amperes. His unit is microampere. Will be. Now we have the two important tools. The power, we will put it at 0. The current, the emitter will calculate 0 microampere, and after that 0.1. The result will be less than, like we're seeing here, less than 0.5, 0.2, 0.3, 0.4, 0.5. All of these will be less than 0.5. And after that, at this point, at 7.7 is 0.7 volts. Here we will dealing with strange phenomena. Here we will note it suddenly increasing in the current. The emitter will calculate high results. If we do comparison with the last results here, like here, all of these less than 0.5, and after that suddenly at 0.5 will be 6, and keep going like that. Here, this, I put it this circle here to say this point, this circle, this thing, this limit or this curve, the appropriate name to it is the knee. At this point, at this knee, we will dealing with suddenly current. We will dealing with suddenly increasing in current. Let's go to another slide. Here, like I said before, we collected the N region with minus power and the positively terminal from the power, AC power, we will put it with the P region, and how the majority in the both sides try to travel to the both of them sides. And here we will explain that at the next slide, why we put always resistors. Then a high current flow, like I said, this column until 0.6, 0.7, the result was less than 0.5, until 0.8. At 0.8, the emitter calculated 6 microampere. Comparison with the last results, this number is huge. Then a high current flow through the diode with little increase in the external voltage. Why? Because like I said before, until 0.6, 0.7, the result was less than 0.5. After that, just we put it more 0.1 volt. After that, the current be equal 8 microampere. Now let's discussion this important thing. This condition represents the low resistance. Like we say, just we put more 0.1 volt, and after that the current suddenly increasing to 8 microampere. What does mean? That's mean here the diode behavior like have has very small resistance inside it, because that this low resistance led to this current suddenly increase to from dots 7 to 8 microampere. The p-n junction allowing very large current, like I said before, to flow through the diode with the only a small increase in the bias voltage. Just we put it more than 0.1 volt and keep going like that. The actual potential difference across the junction or diode is it constant. The action of the depletion region, depletion layer, the same thing. We calculated it or take it like that from the source, approximately 0.3 volt for germanium and 0.7 for silicon. Since the diode can conduct infinite current above, the important thing here, the diode will behave like short circuits. Since the diode can conduct infinite current above this knee point, this the point, the knee here, this circle, sorry, this area is the knee. After that, after this point, after this knee, the current jump to 8. Since the diode here, this important, let us discussion why we put resistor when you use diode like that with our electric circuits, and what the relation between these resistors with our devices. Like we see here, always we put some resistance with different number like we want. The resistors can protect our devices from many damage. Why? Because when we're dealing with phenomena like that, we facing small currents will come back to the device or to our device by somehow, because that resistor will be something like filter to prevent this current. This current have name the leakage, the leakage currents, to protect our devices from leakage current. Here, the resistors are used in series with the diode to put limit to the current flow. Exceeding its maximum forward current specification cases the device to dissipate, to take, to can put some power, to put some limits to the temperature, more power in the to put something like checkpoint on the more power, not in the temperature, I'm sorry, and the form of heat than it was designed for, resulting in very quick failure of the devices. Here, this is very important. By using this diagram, we can do compression between the forward bias and reverse bias, forward bias and reverse bias. Here, the reverse bias, and here this circle, circle is the knee, and this line prevent the leakage current, represents the leakage current, and after that, until here, the diode will behave like resistor. Until this point, after the knee, the diode will behave like closed electric circuit. Here, the diode will represent like very small resistance. After that, we will dealing with suddenly increasing in current. Here will be like short circuit. Here, the potential barrier to germanium 0.3, potential barrier to silicon 0.7, and from the both sides, we will calculate the emitter by using we will calculate the current by using the microampere units. That's it. Our lecture today is finished. Thank you about your listening, your patience. Today, the forward applied bias was the second kind of applied bias. That's it. Let me stop recording.